Hello everyone, and welcome to our series of GARCH discussion. Yesterday, in the last video, we finished talking, ended while we talked about phi GARCH, and we have also seen some examples applying phi GARCH, which was quite important, quite essential. Because we have talked about how we can use one endogenous variable and how the effect of an exogenous variable is captured in the GARCH model, so we can estimate parameters of the GARCH model, whether that is own variance or sigma square. So we generally had two variants. One is capturing the lag of the variance, conditional variance, the lag of the conditional variance, as well as the variance located, capturing GARCH. And so we can actually estimate parameters with the effect of another variable. And basically you can, if you are simulating your series using the estimated variables, you should get back to your variable of interest, and a lot of information can be found from there. Now today we are going to start talking about something very important, which is LR test, or likelihood ratio test of day of the week effect. And we have learned that in our GARCH model conditional variance specification, we can include another additional variable which can actually capture trade volume, policy announcement, day of the week effect. So we'll see a real life day of the week effect information. So consider a GARCH 1-1 model of the financial returns where y equals v, as we know, and sigma square is our GARCH model. And first is the ARCH specification, which is capturing the returns alpha 1 v square minus 1. Then we have the specification or parameter, which is capturing the variance, lag of that variance itself via 1 by expanding the variance, the series. So beta 1 sigma square minus 1. So up until this our GARCH model ends. Then we have the additional lambda 1 d1t plus lambda 2 d2t plus lambda 3 d3t plus lambda 4 d4t, which is our day of the week effect. The other effects are coming into play. Here d1t, d2t, and d3t and d4t are all dummy variables corresponding to Tuesday, Wednesday, Thursday, and Friday, taking the volume of 1 in the appropriate day and 0 otherwise. So this is dummy variable. We are probably going to create a series of dummy variables. A test of day of the week effects is given by the hypothesis. So lambda 1, lambda 2, lambda 3, lambda 4 equals 0, no day of the week effect, or all these at least 1 is not equals 0, which is day of the week effect. So you can easily create dummy variables in 4 different series, keeping the Tuesdays equals 1 only, Wednesdays equals 1 only, Thursdays and Fridays equals 1 only, and you can do it with a loop function, with a logic function, anything you want, or simple logic function. A simple logic function would be fine enough. When FTSE data from example 20.5 are used, the unrestricted model yields a value of the log likelihood value of this function, whereas the restricted value is t log function of this. Now which is obtained. So we have one unrestricted and restricted, two different values for log likelihood function from unrestricted and restricted table. And basically using this we tried estimating the model ourselves. The likelihood ratio test suggested that under the null chi-square the p-value is 0.697, and we are failed to reject the null hypothesis of no day of the week effect at 5% level. So there is day of the week effect on the system. To construct a LM test of ARCH where explanatory variables are included in the model, the assumption of normality enables the test to be implemented using two least square regressions. because the information matrix is separated into two blocks. This is interesting, and we have studied that always, because our information matrix has always been giving us two least square regressions. Information matrix have always been separated into two blocks. The first block contains mean parameters, which are lambda naught and gamma naught and gamma 1. The mean parameters only for each of these parameters, and the variance parameters are captured in the second block, which is alpha naught, alpha 1, beta 1, lambda. The steps to test for arch of order q in particularly this model, where we have an additional gamma 1 xt, is this, right? General arch model. Regress y. So what are the steps? First, regress y on 1 and x and compute the least square residuals v. Fine. Then regress residual v square on its lags. Compute TR square from step 2 and corresponding p-value using chi-square distribution. A p-value of less than 0.05 is evidence of arch in y at the 5% level. So this is just testing on the evidence of y, on the evidence of arch in our model. So this might always be the first step. If we can always try and find if our model has a GARCH in it. If there is GARCH, only then we can go on estimating the parameter, and then with the parameters we can simulate the series, which will suggest if there is a shock in our series, how long it will take for the system to become stable, right? So that is important information. So asymmetries. So this is robustness to begin with, and this is important information. We need to always start with testing our hypothesis, testing our model, our series, if models is specified in our series. The GARCH model assumes that negative and positive shocks have the same impact on volatility, an assumption which ensures that the NIC of the GARCH model, like the arch model in figure 20.3, is symmetric, so we don't have any negative, so this is always positive, just like dy spillover index. A natural extension of the GARCH model is to allow the effects of negative and positive shocks on the conditional variance to differ. So now we can be able to focus out the negative and the positive, or single out the negative and the positive separately. This is especially important in modeling equity markets, where negative shocks are expected to have a relatively bigger impact on volatility than positive shocks as a result of leverage effect. Beautiful information, right? So now we're going to talk about asymmetry. So we have talked about positive shocks, all shocks converted to positive shocks, and we have tested our model. Now we're gonna try capturing negative shocks as well. One way to model asymmetries in volatility is the threshold GARCH or TARCH model. The variance, so we want to capture the negativity, okay, in the series, in the GARCH model. So the variance is now specified as, first we have the arch specification, then we have the GARCH specification, then there is an additional specification for T GARCH, which is phi whisker minus 1 dt minus 1. Now dt minus 1 is a variable given by a dummy variable, and the dummy variable takes 1 if the variance is less than 0, is given 0 if variance is greater than 0. So that's the dummy variable, and that we need to specify ourselves with a logic function. So T GARCH model only if phi is greater than 0. So phi has to always be greater than 0, and that value of d will be less than will be 1 if the lagged v is less than 0, and it will be 0 if the lag v is greater than 0. the effect of positive shocks when the lag value is greater than or equal 0 on volatility equals to alpha 1. So effect of positive shocks on volatility equals alpha 1. That's something we always know. Whereas the effect of negative shocks when this lag value is less than 0, that means minus. Here it means when there are any negative minus numbers, we get 1. On volatility effects equals alpha 1 plus phi. Okay, so now we have alpha 1 plus phi, and that is important information. So what we are doing in a what is the purpose of a GARCH model? We want to capture the negative impact of shocks on volatility. Okay, and because leverage effects such as negative effects generally generally have a bigger impact on our volatility than positive impacts, and so we want to capture the negative impact with a GARCH model. And what do? We extend the general GARCH model with another specification. The specification has 3 elements. One is phi. Phi is the power of the element, the lagged variance Vt minus 1, and dt v square minus 1, which is the lag variance squared, and dt minus 1, which is a dummy variable. Now the dummy variable captures the effect of negativity and positivity by capturing your lagged variance. If lag variance is less than 0, which means your lag variance was minus, then it will be 1, and if your lag variance is plus, then it will take the value of 0, d. And when that happens, first of all, if your lag variance is positive, then you get alpha as the positive shock. The effect of positive shock is captured by alpha, and if your lag variance is less than 0, the effect of negative shock on volatility is captured by alpha 1 plus phi. Now there is another important thing we learned. If you're estimating parameter, we can actually estimate the effect of positive and negative shocks on our parameters. If falls in the equity market are followed by relatively high volatility, then phi is greater than 0. Phi will always be greater than 0. For the case of P equals 1 lag, these features of the model are conveniently, if positive we have alpha 1, if negative we have alpha 1 plus phi. That's all. So these particular parameters will capture the effect of shocks on volatility. If you draw the line or plots, it will actually give you the effect of shocks, and that's amazing, right? The effect of phi not equal 0 is to make the NIC asymmetric. The GARCH model can be estimated using maximum likelihood, and a test of the model can be conducted using wild test of hypothesis phi equals 0 or phi not equal 0. That's all. Very simple. So we can check for phi, if phi is 0 or not, and if phi is not 0, that means there is existence of GARCH model. Then we can go on estimating the GARCH parameters from our model. An alternative asymmetric model of the variance is the exponential GARCH model of Nelson. An example of exponential GARCH or GARCH model is log of sigma square equals alpha naught plus alpha 1. You see Vt minus 1 has always been there, divided by sigma t minus 1 plus phi Vt minus 1 sigma t minus 1 plus beta 1 log of sigma square. So this is the GARCH parameter, I guess. Yeah, and log of sigma square, because log of sigma square is there in the numerators of alpha 1 and phi. We have lagged sigma in both cases. So Vt minus 1 divided by sigma t minus 1 plus Vt phi multiplied to Vt minus 1 divided by sigma t minus 1. The symmetry in the conditional variance is governed by the parameter phi. Indeed, it has always been governed by the parameter phi, and phi helps us to test if there is TARSH available in our model, and phi is so if there is a fall and then relatively higher volatility is found, phi is greater than 0. So as it is the logarithm of the conditional variance that is being modeled, the GARCH conditional variance is constrained to be non-negative for all observations. Because of the logarithm, the conditional variance is non-negative, just like dy for all observations, regardless of the sign of the estimates. This feature of the GARCH model simplifies estimation, and as there is now no need to constrain the parameter estimates to be positive to ensure that the conditional variance is this feature of the GARCH model simplifies estimation, as there is now no need to constrain the parameter estimates to be positive to ensure that the conditional variance is non-negative at each t. But I don't understand this line, because we have always been finding positive estimates, and the purpose was always to be able to find a negative estimate so that we can capture the effect of a fall. Okay, and I guess that was important, but we are constraining the sign with an GARCH model. Okay, so let's see how this goes. There is high possibility that we will have problems associated with this. So we're in page 20 and our problems are located in page 45. This is a big chapter. So we have solved up until 5, GARCH and NH, GARCH and NH. Okay, so testing the day of the week effect is the 6th problem. We can see if there is testing day of the week effect. Okay, and modeling risk. But we don't have a TARSH model exercise, do we? We have a GARCH M, but there is no TARSH. We have a GARCH problem, GARCH M problem. Seasonality distribution. Okay. Modeling risks, which is modeled with GARCH M. So I guess GARCH M is more important. Okay. Midas is very important problem. And then comes multivariate models. Okay, so we have just been talking about the theories, because I don't think there is any actually application shown with GARCH M and GARCH. So because there is GARCH M there, we don't have any applications being shown with GARCH or TARSH. I think the dummy variable is needed to be set up manually, and that's fine. There's no problem with that, because if I'm to do a TARSH model where dummy variables are set up manually, I can easily create a vector D if our parameter values are negative. Basing on that, I can create another vector phi, and then I can jack them into the model, and I will be able to get something. So Gaussian mean. An important application of GARCH class of volatility model is in modeling the trade-off between return and risk of an asset. Wow. this is very important, I guess. Return and risk of an asset. Mu is equal to gamma naught plus phi sigma p, where gamma naught, phi, p are parameters. All of them are parameters, right? So the expected return is mu and the risk is sigma. P is the order, okay, of lags. So what I'm trying to say that I'm trying to model a trade-off between, or a relationship between gamma naught, a trade-off between gamma naught, a trade-off between mu, which is the return, along with the risk, which is sigma. And the equation that I'm drawing with these two parameters are mu equals, obviously first comes the intersection or intercept, which is gamma naught, plus then comes sigma for up until its order, which is the risk, and the coefficient that governs sigma is phi, right? No, it's not phi, it is again, yeah, I mean epsilon, right? Epsilon. The relationship between the risk and expected return of an asset depends upon the attitudes towards risk of asset holders. I know, risk attitude, risk taking attitude. So there are three categories of risk behavior we can find by the risk behaviors, assuming the lags are, there are lags in the system. First of all, some people who would avoid risk, for them the epsilon is positive, greater than 0. Some people whose risk is neutral, if that is so, who do not, who is risk doesn't care, so for that epsilon equals 0, and if epsilon equals 0, then your risk becomes 0. There is no effect of risk in your mean or on your return, okay? Then people who take risks, they get a negative value for taking risk, negative value of sigma, because their epsilon is less than 0. That means mu kind of gets a negative estimate. The GARCH model provides a natural and convenient way to model the dynamic trade-off between the expected return and risk by simply including the conditional standard deviation sigma into the conditional mean. Yeah, that's something we have already seen. This model is known as the GARCH M and is given by, obviously we are talking about y equals mu. Now we are talking about y equals mu plus v, because v captures mu plus v. No, I'm sorry, we have always been talking about y equals v because we're talking about variances, and variances is our independent variable. But now we add the variance with mean, which is our return, because the return is dependent on risk or not. And we know the return equation. We know sigma square is the GARCH model. The second equation gives the relationship between return and risk, and the third equation gives the dynamics of conditional variance, assuming a dynamics of the conditional variance sigma square, assuming a GARCH 1-1 process. Beautiful. The parameter theta, if we can estimate sigma, we can estimate the risks in that particular parameter or asset. The parameter theta equal to gamma naught plus phi or epsilon. It's not phi, I'm sorry, gamma naught plus epsilon, which is the governing coefficient, which takes on the different values for risk attitudes. Rho alpha naught, alpha 1, alpha naught, alpha 1, beta 1. Okay, alpha 1 comma beta 1. This is not alpha 1 beta 1. So alpha 1 and beta 1 coming from the GARCH model can be estimated by, so I'm interested in knowing this one, this parameter because it's the risk attitude. And when are the risk spot is positive and negative, I want to know for a particular stock price. Can be estimated by maximum likelihood methods as usual, and hypothesis test can be performed to test the hypothesis embodied, for example, in equation 20.41. Risk in the term structure of interest rates. I'm going to estimate risks. Beautiful, right? A GARCH model is estimated using daily interest rates on United States zero coupon bonds from 10 October to 28 December. So there is 3,307 data for the 10-year yield and 3-month yield. The estimated model is for return is this is the model. So this is the return model. No, sorry, this is the 10-year yield, which equals an intercept plus a 3-month yield, intercept plus a 3-month yield plus the variance plus VT. So this is the risk plus VT after estimating. So this is 0.117 is the risk parameter, capturing the risk. And then we have the regular GARCH estimation. Standard errors based on Hessian are shown in parentheses. The point estimate of the risk parameter is positive, providing evidence of risk aversion. So a test of the hypothesis is not testing for hypothesis y equals 0 if y is greater than 0 is based on wall test. P-value is providing strong evidence against the null of risk neutrality. So null is risk neutral, so we don't accept null, we reject null. So people are mostly risk averse, which is a good test indeed. Let's see how this goes. Okay, so we are to back in page 22, but before that let's go to page 47, and we have day of the week effect in equity returns. So GARCH seasonality, and we're gonna start reading GARCH seasonality and GARCH M. So let's open these. GARCH seasonality and GARCH M for in MATLAB first. I'm just gonna pause it at this moment and set the theater up, and then we're gonna come back. Let's see how GARCH seasonality comes into work. So we are talking about GARCH 1.1 model, where we have sigma square, our conditional variance equals to GARCH. Then we have the day of the week effects, which is the dummy variables, and y is the zero mean percentage return on FTSE, and the the dummy variables corresponding to these 4 days of the week. We want to do a LR test for seasonality, likelihood ratio test, to see if we have the facts of week on our data. And I want to include an holiday dummy variable and perform a joint test, and I want to do that for Dow and Nikkei. Okay, so obviously this is the equation that we need to remember, and obviously we will start with passing our functions. So first, because we're talking about likelihood ratio test, we will have two things: unrestricted and restricted conditional variances. So first of all, see unrestricted conditional variance. And what am I finding here? What are my parameters? My parameters are b, y, right? b, y, as we already know, we have studied that before. Then the dummy variables. So b, y, and all these dummy variables for all these different dates are my unrestricted parameter. So obviously u equals y just before. Then the dummy variable is well, the fourth 1 2 3 dummy variable starts from the fourth parameter. which is squared. Fourth parameter, yeah, dummy variable is appearing in the fourth parameter, which we are squaring and multiplying with the user dummy variable. Then obviously we are talking about variances with parameter, because this is basically lambdas are basically being squared, because this is being squared. So these dummy variables are being squared and multiplied to variances are being squared, we can say that, and multiplied to these 4 days, right, to see which day we have an effect. Then comes our GARCH, and we start with a REXRR model, which is a recursive function. And what does a REXRR takes in? It takes x, exogenous variable x, then y naught, the initial initialized value, the initial value, and then a is the autoregressive parameter. Okay, so ARP. So first we have b1 square, which is the GARCH portion basically, then b2 square. But first we have, okay, all of them we are squaring. So first we have b1 square, then b2 square, trimmer 0, u square 0 1. So multiplying with trimmer, we already have u square from y. We start with the 0, and after 0 in the same column we have rest, we have is u squared value or y squares, all of them, all the variances basically. So first we have b1 square, then we have b2 square applied on a series, and I'm trimming the first one, that is 0. I'm trimming nothing from the first one, I'm just trimming the last value, okay, from that. And d is coming from the dummy equation. So this is our x, this is how we are estimating x. So we started with beta 4, and from beta 1 we are using a beta 1, beta 2 our parameters, and beta 3. So how many parameters did we have? Beta 1, beta 2, beta 3. So beta 1 alpha naught, we are squaring everything for now, let's just remember that. Beta 2 alpha 1, beta 3 beta 1, and I want to see the effect of dummy, which starts from beta 4, okay, and all of them are being squared. So beta 2 is again being squared and being trimmed, and in beta 3 okay, 0 and u square, right, which would mean that this is representing our u square, and then comes d. Okay, this is our x. Then y naught is standard deviation of well, that is the unconditional variance basically, and lag value p, which is this one, okay, beta 1 representing the lag coefficient, which beta 3 squared, okay, beautiful. And then z is simply, you know, u divided by square root of h, which is standardization, and log likelihood function is half log twice by half log sigma square, or the variance itself, and z square, u divided by square root of h whole square, that's all. So u divided by sigma square whole square, square root of h whole square, that's all, and that's fine. In terms of restricted model, again we do that, but again in restricted we don't have the dummy variables, except that we have everything as it is, nothing changes. Or how do you deal with that? Is there any difference I'm gonna talk about? Yeah, column bind. You see, this is a thing in R. Under XRR beta 1 square, we are doing column bind, we are bringing everything in columns. The first column beta 1 square, so you're doing the results should be in one column, that is x. So let's bring everything in one column. then row bind trimmer, then okay, this is the first row, then this is the second row, so bring everything in one row. Okay, bring everything in one row, then just fix it. So column bind brings everything under one column, row bind connecting the rows, where column bind is connecting all of the rest of the stuff. Okay, the whole model. Then standard deviation u square is being column bind brought in one column, this is brought in one column. So vectors, we're vectorizing with column bind, we're vectorizing with row bind to it, displacing rows, that's all. And this function I'm willing to return lf. Here is same thing, so let's just return lf, let's just return lf. Okay, beautiful, not difficult at all. And let's see how the actual one works out. So I'm loading the and then I'm loading my data, and obviously now nothing is in metrics, you have to convert the data in metrics, you have to read the table, and then you have to pass the column names as this. I mean, you have to create this, you know, vector that was passed as a column name, as column name. So there's a lot of things. Tuesday dummy, Wednesday dummy. As I told you that whenever we can create dummy variables manually or with a programming language, whatever it is, and that's gonna be very simple. We can simply do it in Excel, it's not a big deal. Anyway, I'm bringing them all in and I'm just naming the column, okay, and then converting everything into matrix. So let's start with the footsie, the first one, and I'm gonna first find the return and risk. Okay, return and risk will come next, let's not be confused at this stage. And then y minus mean y is y, you know, from the percentage return calculation, and t is equal to length of y. Fine, let's just stream the dummy variables. So for Tuesday, because I want everything to be in the size of the xrr function, and remember first we put 0 in the xrr function for our initial value. We started with 0, which is an unconditional variance estimate. So first, for everything, just to fix the dimension, I'm trimming. Okay, you can have a look and you can do it yourself, it's not a big deal. Then the thing comes, let's just pass the GARCH model. We can start with any number we want depending on what variable, how many parameters we have. We had quite a lot of parameters, about 7 parameters. We pass the initial value for all the parameters, right? And we do neglog b, y, Tuesday, Wednesday, Thursday, Friday, Wednesday, Thursday, Friday. So start by. Basically Thursday, Friday, yeah. So we have the log likelihood function from our optimization. What is bothering me is that I'm not sure why there is 7 parameter initialization here where there should have been 6, right? Because we have always been dealing with 6, so that must be a mistake, an error, I guess. I'm not sure. Okay, just leave it as it is. Let's not think about it. Let's also delete it right now. Okay. And we have optimization. We run it, and LF1. We have the log likelihood function. So we have estimated all the parameters, right? And remember, one important parameter is alpha 1 that captures what? The effect of shock on your variance. The effect of shock on your variance is captured with alpha 1, and hence that is a really important parameter. By, oh no, I'm estimating beta. Oh yeah, we have, obviously there will be 7 because beta, how many betas are there? It depends on that. We had 7 betas in our functions. How many betas we had? We had 7 betas indeed. That's why, because we want to find alpha, not alpha 1 and beta 1. 1 2 3 4 5 6 7, alpha naught, alpha 1, beta 1. So wow, beta and y makes it even bigger. So we're estimating in terms of betas. Fine, alpha naught, beta 1, beta. That's why if I have reduced 1, there will be an error. So with beta, when the results of beta comes out, we see alpha 1 is there, which is very important. Effect of shocks and how long it takes. And then without seasonality, alpha naught, beta 1, alpha naught, alpha 1, beta 1. That's all we have. And we can do a likelihood ratio test to see if there is any effect of seasonality in our system or not. So that is the GARCH seasonality problem. Then looking into GARCH M would be more interesting, because now we're gonna find a relationship between risk and return. Modeling risk in the term structure of interest rate. The data consists of daily yields on United States zero coupon bonds. Okay, the returns as a percentage over the period of this period, a total of 3000 observations. The maturities are different. So we have, first of all we have the return, which consists of, obviously that is equal to the variance, because we're dealing with the variance. This is a autoregressive conditional heteroscedasticity model, plus the return, mean return, which captures the risk factor as well. Where is the risk factor in this equation? So first of all, we have lambda naught, lambda 1, phi sigma b. Now epsilon sigma b, and epsilon can take up 3 values if your investor is risk averse, non risk taker, or risk neutral. Depending on that, if he is risk averse, epsilon is greater than 0. If he is risk neutral, is epsilon equals 0. If he is risk taker, epsilon is less than 0, and hence sigma represents the risk, whereas gamma, this is the return, and the relationship is drawn with gamma 1, gamma naught, gamma 1 R3M T for 3 year. Probably this is just for the 3 year thing. Born the 3 months. Sorry, yeah, starting with 3 months only. 1 year, 3 year, 5 year, 7 and 10 year. I'm not gonna be concerned with other data. And then the GARCH model is coming into play, and this is what I need to be concerned with. Gamma 1. What is bothering me is page 48. I'm talking about gamma 1, right? And obviously there was this in GARCH M. Okay, if positive alpha 1, oh, gamma will capture the fact actually, because if variance is positive, we have just alpha 1, the shock of positive, and the positive and negative shocks. Oh no, that is something else. Is that GARCH model I'm talking about? Yeah, GARCH model. Let's talk about GARCH M. Okay, you see, this has not been discussed. This is just a coefficient estimate. Coupon bond for this is just a 10-year yield and 3-month yield. Zero coupon, we are taking 2 variables here, 10-year and 3-month, and we are just drawing the relationship, variance for 10-year and 3-month, and that's all, nothing else. Okay, so that's it. Okay, and then the GARCH is there, where R10 is the 10-year and R3 is the 3-month yield on United States zero coupon bonds. Perform a test of risk neutrality. Perform a test of linear risk return relationship by testing the restriction rho equals 1, and then we can choose simultaneously choosing 1 or 3 or 5 or 7-year bond yields as the dependent variable. Okay, not the independent variable. Okay, we can choose 1 year, 3 or 5 year and 7 year respectively as dependent variable. Basically, yeah, this is a dependent variable. So first I'm working on 10-year. On bonds are 3 month, 1 year, 3 or 5 year, 7 year. I can change it for 1 year, 3 or 5 year and 7 year, and see what happens. Okay, fine, why not? Let's see how this looks. So obviously, starting with the function, log likelihood function, what do we have? We have beta, which is coming from, obviously, beta will have gamma naught, gamma 1, all of them actually, quite a beta. There is basically 7 betas, right? So what are the betas? Gamma naught, gamma 1, alpha naught, alpha 1, 1, 2, 3, 4, 5, 6, epsilon, beta 1, 7 is probably mu, or V, probably V. So let's see. Then R3M and R10, all of them we want to estimate 3 month and 10 year. B is absolute value, T is length of 3 month. Let's just take length of 3 month. M is zeros, T rows on column. Y, because we're not gonna use a for loop somewhere. U is 0. So there are 2 equations. So for different equations I'm gonna do for loop. H is standard deviation of the difference between 10 year and 3 month being squared, variance multiplied to once. Okay, so basically we have the GARCH equation. So we have 3 equations for 2 to t. First we have the GARCH equation. So beta 1, beta 2 u square, beta 1, beta 2, alpha naught, alpha 1 v square, and beta 3 I minus 1, which is v square, and then I minus 1 sigma, not squared, because H is GARCH. GARCH is already in the variance form. So u square, but H I minus 1. Then comes M, the second equation. And what do we have in the return equation? The risk factor will be captured here. Beta 4, indeed. Then beta 5, 3 month. Beta 6 is epsilon. Beta 6 is epsilon. And we have what? Beta 6 is epsilon. And root over hi. Okay, so we have the conditional variance already estimated here. We take a root, because to the power 0.5 is the root, and that is squared with the lag value p. Simple. So first we root it down, square root and lag value p. So we are concerned with finding here the variance here. Okay, hi, because hi will capture the risks associated with these parameters, right? Not, yeah, hi will capture the risks. Oh, no. Yeah, mu is the equation that has risk and return. hi will capture the risk, and then R10 minus mi. So R10 equals u minus m, R10 minus mi. Just simply fix this equation, regular algebraic equation. Then we do the log likelihood function. Now let's do the whole thing together. What is So replicate 0 t times, replicate 0 t times, that's all. This all same thing, just return LF at the end. We take the data in, we do it for 3 months. I mean, we single out 3 months in the 10-year data. 10-year data is dependent. We do pass these. We take some initial values as estimates. Starting values are close to the maximum likelihood estimate. Okay, fine, but I haven't done the maximum likelihood estimate yet, so just some starting values, initialization, so just some initial values. Then I'm gonna run the maximum likelihood estimation. I'm gonna find theta values, obviously, but I'm gonna find the risk factor here, gamma, rho, blah blah blah, and wall test for risk neutrality. I can do theta 6, which is which one? 1 2 3 4 5 6. Basically theta 6 would be, which beta is theta 6? So many betas are there. Theta 6 is epsilon, right? So theta 6 is epsilon. So I'm gonna check for okay, yeah, I'm gonna check if there's epsilon there or not. So theta 6 minus 0 square divided by variance covariance 66. So this is the wall test is coming from the regular wall test equation. We're in 48. Let's go up to 20, and yeah, we test for wall test is given by our epsilon value minus 0 divided by 0.20, which is the epsilon's standard error. That's all. This is the epsilon standard error. Yeah, epsilon value minus 0 divided by epsilon square divided by epsilon standard error. And from Hessian we can find that, right? So that's how inverse VC, the 6th row and 6th column. In the 6th column is located, there is the standard error of the epsilon. We do it and we have the risk neutral. If it is risk neutral or not, then we can also do for theta 7 if there is risk return relationship, which is theta 7 in our equation is B7, which is the lag parameter. No? So var epsilon and rho, yeah, the lag parameter, right? Yes, correct. So that's it. Let's run it and see what happens. If anything that happens, I'm not sure. So it's running, I guess, and we get some risk parameter estimation, and basically we can take a big for loop and put this under the big for loop, and this will continue for very long time. Okay, then so basically we have covered up until problem 7, which is pretty good. We're going at a good rate. Then we still have quite a bit of to go, especially if we are willing to talk about there's still things that will be more difficult in the coming time. So this is a huge chapter. See, the iteration is happening, and we have the epsilon values 0.116, which is pretty good. and we can do this for a long period. I mean, we can put this all in a for loop and see what happens. We'll have the risk graph from this. Not bad. The risk graph from our return, and the risk return relationship is drawn. Okay, plan is to use this to find the risks, not how quickly shock absorbed the risks on these parameters, and see how things happen. But obviously we need a dependent and an independent variable. So our dependent can be US stock price, and our independent variable can be oil price. Beautiful. Or commodity. Instead of stock, we can deal with commodity. R3 and R10 commodity. Yeah, beautiful. Thank you very much. And here probably I'm gonna draw a line for today, and we can come deal with more problems. We're gonna take some time later. Thank you.